Welcome to the video on semiconductors. Today's topic is electrons and holes. The mechanism of current conduction is relatively easy to visualize in case of metals. So the metal atoms are embedded in a sea of electrons, and these electrons can move freely under the influence of an applied electric field. This free electron view is simplified, and important conduction properties of metal can be derived from this basic model. However, we cannot account for all the electrical properties of semiconductor in this way, since the semiconductors has a filled valence band and an empty conduction band at 0 degree Kelvin, and we consider an increase in the conduction band electron by thermal excitations across the band gap as the temperature is raised. In addition, after electrons are excited to the conduction band, the empty states left in the valence band can contribute to the conduction process. The introduction of impurities also has an important effect on the energy band structure and on the availability of the charge carriers. Thus, there is a considerable flexibility in controlling the electrical properties of semiconductors. So, now we will be discussing what is meant by electrons and holes. As the temperature of the semiconductor is raised from 0 degree Kelvin, some electron in the valence band will receive a sufficient thermal energy to be excited across the energy gap to the conduction band. The result is a material with some electron in the otherwise empty conduction band and an unoccupied state in the otherwise filled valence band. For convenience, an empty state in the valence band is referred as a hole. If the conduction band electron and the hole are created by the excitation of an electron from the valence band to the conduction band, then the pair is called as electron hole pair or abbreviated as EHP. After excitation up to the conduction band, an electron is surrounded by a large number of unoccupied energy states where it is free to move. For example, the equilibrium number of EHPs in pure silicon at room temperature is only about 10 to the power 10 EHP per centimeter cube, whereas the silicon density is 5 into 10 to the power 22 atoms per centimeter cube. Thus, the few electrons in the conduction band are free to move about via the many available empty state. The corresponding problem of charge transport in the valence band is somewhat more complicated. However, it is possible to show that the effect of the current in the valence band containing holes can be accounted for by simply keeping track of the holes themselves. So, what is a hole? Hole is nothing but the empty space. For example, consider an insulator or a semiconductor with a few electrons excited from the valence band into the conduction band. By applying an electric field, now the electrons in the valence band will have some energy into which they can move. If we describe such changes via the movement of the empty state, then that is called as the movement of the hole. So the deficiency of the negative charge is called as hole, and hence holes are called all the positively charged particles. So, when coming to the current density, to account for the movement of the charge carriers in the formation of the current, we will consider a field band where all available energy states are occupied. For every electron moving with a given velocity, there is an equal and opposite electron motion elsewhere in the band. If you apply an electric field, the net current is zero because for every j electron moving with a velocity vj, there is a corresponding opposite electron j dash with velocity minus vj. So here, if you take this in this diagram, if you take the electron whose charge is given as kj, it will be having an equivalent opposite effect which is called as minus kj. So in this case, the jth electron with wave factor kj is matched with a by an electron at j dash with opposite wave factor minus kj. So finally, there is no net current in the band unless an electron is removed. Okay. Now assume that there are n electrons in the band, then we have expressed the current density using the sum of over all the electron velocities and including the charge minus q on each electron in a unit volume the unit volume, the current density is given by J is equal to minus Q into summation of I is equal to 1 to n Vi is equal to 0. So here for each electron we will be having n opposite minus Vj, and Q is nothing but the charge of the electron. Now assume that we are creating a hole by removing the jth electron. The net current density in the valence band involved sum over all velocities minus the contribution of. So here J is equal to minus Q into summation of I is equal to 1 to n Vi, which is nothing but the current due to the electrons, and minus Q into Vj, which is the jth electron which is missing there. So in this, of course, the charge transport is actually due to the motion of the new uncompensated electron. Its current contribution is minus Q minus Vj is equivalent to that of a positively charged particle with velocity plus Vj. For simplicity, it is customary to treat empty states in the valence band as charge carriers with positive charge and positive mass. So next, we will be discussing about the analogy of the holes in a semiconductor. Consider we have two bottles, one completely filled with water and one completely empty. We can ask, will there be any net transport of water when we tilt the bottles? The answer is no. In the case of the empty bottle, the answer is obvious. In the case of completely filled bottle also, there is no net motion of water because there is no empty space for water to move on. Similarly, an empty conduction band completely devoid of electrons or a valence band completely full of electrons cannot give rise to the net motion of electron and thus to the current conduction. Next, we imagine transferring some water droplet from the full bottle into the empty bottle and leaving behind some air bubbles. And now if we ask ourselves the same question. Now, when we tilt the bottles, there will be net transport of water. The water droplet will roll downhill in one bottle and the air bubbles will move uphill in the other. Similarly, a few electrons in the otherwise empty conduction band moves opposite to an electric field, while holes in the otherwise filled valence band move in the direction of the field. The bubble analogy is imperfect, but it may provide a physical feel for why the charge and the mass of the hole have opposite sign from those of the electrons. So here, in the following discussion, we shall concentrate on the electrons in the conduction band and on the holes in the valence band. We can account for the current flow in a semiconductor by the motion of these two types of charge carriers. We draw the valence and the conduction band of the electron and the energy scale. However, we should remember that the valence band hole energy increases opposite to the electron energy because the two carriers have opposite sign. So, we have discussed what is meant by electrons and holes in a semiconductor, and how the electron and holes will be having opposite charge, and electrons are negatively charged and the holes are the positively charged particles, and always they move in the opposite direction. So in the next video we will be discussing about the intrinsic and extrinsic semiconductors. Thank you.